Okay, here we want to talk about the rules of limits. So we have the following rules. Well, first, we have that the limit of a certain function f of x as x tends to a point c is L, and then the limit of another function as x tends to that same point is called M. So we want to look at the following rules, and then we will look at these few examples as we apply the rules on it. Great. Now the first rule tells us that when we have a constant multiple with a function, that is k times a function of x, right? So this k is just a constant. For example, you can say 2 times something. If you have a function of x, let's say a square root of x plus 1, then you multiply that with 3. That 3 is a constant multiple. So if you have a constant multiple with a function, then the limit of the whole of that function is going to be the same thing as you pulling the constant out of the limit notation and taking the limit of the function on its own. Great. So you just multiply the constant with the limit of that function, and this is what you will get, given that the limit of the function is called L. Alright, the second rule tells us that when you take the limit of the sum or difference of two functions, that is f of x and g of x, then the limit of a sum of two functions is the sum of the limits of those functions. Remember that the limit of the first function is L, and then the limit of the second function is M. So the limit of the sum of two functions or difference of two functions is the sum or difference of the two limits. Good. And then the product, limit of product is the product of limits. Then for the quotient, we have that the limit of the quotient, this divided by that, is going to be the quotient of the limit, but provided that the denominator is not 0. You know, when we have a fraction, we do not want to divide by 0. That is, the denominator of fraction is not allowed to be 0. Good. So that is why I'm making this observation. So the fifth rule tells us that when we have the limit of an identity function, now whenever we have f of x, let's say a function of x to be just x, right? This is an identity function. Reason being that if you impute 2 here, you know this is just x, it gives you that 2. F of x gives you x. So for any input, f of that input will give you the result to be the same thing as the input. That tells us that f of 2 is going to be the same thing as 2. That's just an identity function anyway. Alright, great. So when you take the limit of an identity function, as the input tends to c, the result is just c. The example 5 will illustrate what we are doing here. Right. So the limit of just a constant as x tends to any value is that constant. So if you say the limit of 5 as x tends to 3 is going to just be 5. Anyway, we'll see that as we get down to the course. And lastly, when we have the limit of a function and you raise that function to some power, right? Great. It is the same thing as taking the limit of the function and raising the whole result to that power. Well, let's just put in some examples and so that it will not be so abstract for you to see. So the first example here will correspond with the first rule. So we have the limit of 2 times x squared as x tends to 1, right? So if you want to look at the structure, you will see that c here is the 1 there. Then the constant multiple with the function part. So this is 2, and this is the function part, x squared. So these two can be regarded as a constant multiple in this case. So we have as x tends to, in that example, as x tends to 1, then we want to evaluate the limit of that function. So from this rule, we see that we can multiply the k outside. So I can multiply these two outside since that is just a constant multiple. We say 2 times the limit as x tends to 1 of x squared. Right, great. Now we have to evaluate this. So as x tends to 1 of x squared. Anyway, to evaluate this limit, we just need to do a substitution. That is, as x tends to 1, we plug in 1 in place of x here and evaluate the function. So this will give us these 2 here times. Now, as x tends to 1, right, just plug in 1 here. 1 raised to power 1 raised to power 2 is going to be 1. So as x tends to 1, x squared, which is 1 squared, tends to 1. That means we're going to have 2 times 1, right? And which that just gives us 2 as a result. Okay, great. So you just need to substitute and do some simplifications, and that's what you'll get. Then the second example here, we want to evaluate the limit of this function using the second rule. We have the limit as x tends to 0 of this function f of x, 4x minus x squared. So, given this rule, sum or difference of two functions, this example focuses only on the difference of the two functions. This is the first part of the function, or that is the first function, 4x, and then the second one is just x squared. Great. So the limit of the difference gives us the difference of the limit. So here we can simply say the limit of this first one minus the limit of that second one, all right? As if we want to distribute. So we say the limit of 4x as x tends to 0 minus the limit of x squared as x tends to 0. All right, so the limit of 4x as x tends to 0 minus the limit of x squared as x tends to 0 is same thing as the limit as x tends to 0 of 4x minus x squared. All right, so 4x as x tends to 0 will be 0, then minus x squared. The limit of x squared, that is this second one, as x tends to 0 will be 0, because you just have to substitute 0 in place of x here. That will be 0 raised to the power 2, which is just 0. Okay, so this gives us 0 minus 0, and that's it for the second question. So the limit of this function as x tends to 0 is equal to 0. The limit of the first function as x tends to 1 is equal to 2. So just by substituting 1 in here. All right. Well, I'm just using it to, I'm just applying the rules on each of them. The third one will be based on the product rule, that when we have the limit of the product of two functions, it is the product of the limit of those two functions. So, we have the product of two functions here, right? So you want to take the limit of the first function times the limit of the second function as x tends to 5 for each case. So, let's look at it. The limit as x tends to 5 of 25 minus x squared times the limit as x tends to 5 of 4 plus x. All right, good. So the limit as x tends to 5 of the first part of the function, right, as I said here, now using the rule that the limit of the product of these two functions is the product of the limits, right? So the limit of the product will be the product of the limit, right? That is just it. And then we take the limit of 25 minus x squared as x tends to 5. Now as x tends to 5, right, x squared will tend to 25. That is, if you say x as x tends to 5, you plug in 5 in place of x here, you're going to have 5 raised to the power 5 raised to the power 2, which is 25. Then we have 25 minus 25, that gives us 0. Right? So we can put this, let me put it down here, 0. And then we multiply it with, again, as x tends to 5, 4 plus x, you're adding 5 to 4, you're going to have 9. So this is going to be 0 times 9. And 0 times 9 is 0. So that tells us that the limit of the whole of that will be 0 times 9, which gives us 0 as an output. Right? Great. So that is the limit of that function, just by using the product rule. Now the fourth question there, we are going to use the quotient rule to evaluate. So the limit of the quotient of two functions, that is f of x divided by g of x, is the quotient of the limit, so L over M. Okay, so using this, as x tends to 1, we are going to have to evaluate the numerator, then the limit of the numerator divided by the limit of the denominator as x tends to 1. So let's just do that anyway. Now we have to take the limit as x tends to 1 of 2x squared plus plus 7x, alright? That is just the numerator alone. So as x tends to 1, as I said earlier, when we have a polynomial function like this, all we just need to do is to substitute that value that we are approaching. So as you're approaching 1, we plug in 1 here, we're going to have 2 times 1 x raised to the power 2. So where x is 1, we have 1 raised to the power 2, then plus 7 times x, where x approaches 1, alright? You just substitute 1. So when we evaluate this, we're going to have 9 as an answer. So that tells us that the limit as x tends to 1 of the numerator alone is 9. Then we just have to do that to the denominator. Okay, so the numerator here is 9. Maybe I can equate this and put 9 on top. Then I divide it with, now we have to check the denominator. So the limit of 5x squared plus 1 as x tends to 1. Alright, so again, 5x squared plus 1. So as x tends to 1, we just substitute 1 in there. We're going to have 1 raised to the power 2, which is 1 again. That is 5 times 1 raised to the power 2 plus 1. Alright, so you observe as x tends to 1, we just substitute 1 in place of x in that function. And then we simplify that. That will be 6. No, 1 raised to the power 2 is just 1. Times 5, that will be 5. Then plus 1, that gives us 6. So that tells us that the denominator here is just 6. The numerator was 9. The denominator is just 6. Maybe we can simplify that a little bit by dividing 3, or dividing numerator and denominator by 3. That gives us 3 over 2 to be the limit, which is actually an improper fraction, but that is okay. Great. But what that just tells us is that if you can say the limit, if you are given the limit of a rational function, okay, let's say of a fraction, you can split them by taking the limit of the numerator and then taking the limit of the denominator, then you divide them together like that. Okay, good. And then we have to consider the number 5, 6, and 7 using the 5, 6, and 7th rule. So the 5th rule tells us that the limit of something, as that thing tends to a certain value, is that value. So the limit of x as x tends to c is just c. Now you look at this, the limit of x as x tends to 10. Using that rule, we can simply know that the answer is going to be 10, right? Again, the limit of x as x tends to c is equal to c. So the limit of x as x tends to 10, so in this case, c is equal to 10. So the result here will just be 10, right? Good. And then the next one tells us that the limit of a constant as x tends to 100 is going to be, the limit of a constant as x tends to c is that constant itself, right? Because that constant is independent of x. There is no way we are going to evaluate this. So the limit of 5 as x tends to 100 is going to be 5. Now that rule number 6, irrespective of what x is approaching, right? Given that the function is just a constant, that is just a certain number, that is what it means to be a constant, the output of our limit does not depend on the input in this case. It just depends on that constant that we have as a function. All right, good. Okay, so the last rule tells us that if you have a function raised to some power, right, the limit of that is going to be the limit of that function, then you raise that to that power. So in this case, we are having the limit of 3x as x tends to 4. Then we raise that to power 2. That rule tells us that this is the same thing as the limit of 3x as x tends to 4, all raised to power 2. Right? Great. So you notice that this L, as we discussed earlier, that it is limit of f of x as x tends to c. That is the L. So limit of f of x as x tends to c, all raised to power n. So that is what we are doing here. So as x tends to 4, you observe that 3 times 4 will be 12, and then you raise that to power 2. Right? Just by substitution, and that gives you the limit of that function. Okay. Anyway, we are going to solve more examples using these rules, but they may be a little bit complicated. But they're not difficult anyway, just by substitution and then I'm noting the rule to make use of. Right, thanks for watching.